Okay, this is lesson 8.6, comparing linear, exponential, and quadratic functions. In the core concept, you've had experience with the slope-intercept form of the linear functions. You've worked with the exponential functions, y is equal to a b to the x power, and most recently we've done quadratic functions with the parabola. So you have experience graphing all of these and describing various parts, for instance the domain and range and so forth. In our first example, if you plot the points, then tell whether the points appear to represent a linear, an exponential, or a quadratic function. So the solution's obviously right in front of you, and this is right out of your textbook. If you plot the points for A, you can see that it forms the parabola and is quadratic. For B, it is a straight line, so it's linear. And C is exponential. So remember about C, it approaches the x-axis, but it will never cross it. So we're going to work through a couple of these. So this example, we will plot, and I'm just going to number the number lines with a 1, a -1, and a 5, 2, and -1, 0, and -1, 3 and 5, and 1, -3. So you can tell already this forms the shape of a parabola. I'll try to connect it with a smooth curve. It's kind of hard to do on the iPad. Not too terribly bad, but you'll want to go through all points. So we would name this quadratic. Okay, let's try another one. Plot the points, tell whether they represent a linear, exponential, or quadratic function. Again, we'll just number them. I'll go ahead and number them with a 1, even though I can see that there's going to be some large values, but with those fractions, I think it'll be the easiest way. So a -1, 2, -2, 8, be about here, -3, 32. It's going to be so far off in the chart you can't see it. How about a 0 and half? And 1 and 1/8. So do your best to draw the line. But this is appearing to be exponential, so it's going to approach the y or the x-axis, but it'll never cross it. So again, this is just describing the shapes of the different graphs. And let's plot this one. And hopefully you can tell that that's a straight line. So again, I'll try to draw the straight line. And we'll call that linear. So in the next core concept, we want to look at the differences in ratios of functions. So we'll use some patterns between the consecutive data pairs to determine which type of function models the data. The differences of consecutive y values are called first differences. The differences of consecutive first differences are called second differences. So I know this sounds very confusing, but once you see the explanation of the example, you'll understand. So in a linear function, we have looked at the patterns before to determine if we had a common difference or a common ratio. And so that we know that in linear functions we have a common difference. And the first differences are constant, meaning that as you look at the change in y, you see a common difference between the y values. In the exponential functions, again, you have experience with this as well, you have a common ratio in the consecutive y values. So we would search for the common difference, and since it's not a constant, then we look to see if there's a factor, something that we could multiply each thing by, and then we know that it's an exponential function. For quadratics, the second differences are constant. Okay? And what that means is that you do the linear function and maybe the first difference isn't constant. And we can't find a common ratio, so then we look at the first differences to see if there's a common difference between them, and we call that the second difference. So that's what I was talking about. So the first differences for exponential and quadratic functions are not constant, okay? And that's when we'll be able to determine if it's, we'll either look for the common ratio and say that it's exponential, or we'll look for the second difference and see that it's quadratic. So in this example, we'll be looking at the differences. So tell whether each table represents the linear, exponential, or quadratic function. So in A, you can see the solution. The x values have the same rate of change. So the common difference is +1, so it's increasing by 1. And for A, the y values are decreasing by 3. Since that's a common difference and it's the first difference, it's a linear function. So we could write that function in slope-intercept form. For part B, the consecutive y values have a common ratio. So the table represents an exponential function. So if you were looking for the common difference in part B, we'd say, 1 to 2 is +1, and then it was +2, and and then +4, and so on. It's not a constant difference, so we have to look for the common ratio, or we have to look then at the common second difference. Okay, so in C, here's what we mean by the second difference. So the x is increasing by 1, but the y, the first difference, decreases by 1, increases by 1, increases by 3, increases by 5. So one thing you could do is possibly look for the common ratio, but we cannot find one. So then you look for the common difference here, and what that means, the second difference between -1 and +1, and this kind of got cut off at the bottom here, is +2. Okay, between 1 and 3 is +2, and between 3 and 5 is +2. Since the second difference is constant, it's quadratic. So here's the study tip. First, determine that the differences of consecutive x values are constant, then check whether the first differences are constant or consecutive y values have a common ratio. If neither of these is true, check the second differences. So we'll kind of first be checking to see if it's linear, then see if it's exponential, and then finally, if it's neither of those, make sure that the second difference is constant in order to determine that it is quadratic. So tell whether the table of value represents a linear, an exponential, or a quadratic function. So in this case, we want to make sure that our consecutive x values Okay. And then we look for our y values. So if I go from 1 to 3, I'm adding 2, and then I'm adding 6, oof, and then it really jumps. So since it doesn't have a common difference, what about a common ratio? So from 1 to 3 would be times 3, from 3 to 9, times 3, from 9 to 27, times 3, right? And don't forget to check the last one, times 3. So since it has a common ratio, it would represent an exponential. Function. Okay, we're going to take it one step further, and this time we're going to tell whether the table of values represents a linear, an exponential, quadratic function, and then we're going to write the function. So first determine which type of function it represents. So first check that the x values are increasing by 1 or by a constant difference. So in this case they're increasing by 2, but make sure that it's constant. Second, look for the first differences. So we're subtracting 12, then subtracting 4, then adding 4, and then adding 12. So one thing that you can tell, I think, pretty easily from this is that the pattern, when we look at our parabolas, we know that they have a lot of the outputs that are the same. So now let's look to make sure the second difference is the same. From negative 12 to negative 4 is plus 8. From negative 4 to plus 4 is plus 8. Positive 4 to positive 12 plus 8. So the second difference is constant, therefore we can verify that it is quadratic. So since we know this, we're going to write an equation of the quadratic function. If you use the table, you notice that the x-intercepts are 4 and 8. Okay? So using the intercept form to write a function. This is from our previous lesson. So let's substitute for p and q in the intercept form, which is y is equal to a times the quantity x minus 4 times x minus 8. Use another point on the table, and you can see that they've used the point 2 and 12, which is the very first one, to find a. So if x is equal to 2, y would be equal to 12, and then the only missing variable would be a. So substitute those values in. A 2 for x and a 12 for y. And go ahead and simplify. So in this case, a is going to be equal to 1. Now that we know that a is equal to 1, use the value of a to write the function. So substituting in 1 for a, use FOIL and combine like terms. So the quadratic function is y is equal to x squared minus 12x plus 32. So let's try one of these to see how we do. So going from, oops, it's not going to like that. Let's try this. Going from negative 1 to 0 is plus 1. 0 to 1, 1 to 2. So we have this constant common difference here as in the x. When we look for the common difference in the y, we will have subtracting 8, subtracting 4, subtracting 2, subtracting 1. So we do not have a common difference for the y. However, if we look at the difference between 16 and 8, well, 16 times 1/2 is equal to 8. 8 times 1/2 is equal to 4. So we have this common ratio. Okay? So from the table, we can see that when x is equal to 0, y is equal to 8. So therefore, a is equal to 8. And the common ratio is equal to 1/2. So you can see that our exponential, first of all, because of the common ratio, we know it's exponential, and I know that you've seen the answer up there the whole time, that you could write it as y is equal to, we'll substitute in the values for a. Okay, substitute in the common ratio, and your exponent is x. And let's just try one more just to make sure. So in this case we have the x values increasing by 1. So we have the constant change for x. Our y values are increasing by 2 every time. So we actually have a common difference. And remember, when we have a common difference, this would be linear. So we have a linear equation. And if you can recall, when we write a linear equation in y equals mx plus b form, we have to calculate the slope or the change in y. So m is equal to the change in y over the change in x. And in this case, it's equal to 2 over 1, or simply 2. If you see the y-intercept, when x is equal to 0, y is equal to 1, we have b. So we could write the linear function y is equal to 2x plus 1.